So good evening everyone. Let us continue our discussion on retrofitting and rehabilitation. So in this fifth week, we will be basically understanding various ways to retrofit a structure using FRP, that is fiber reinforced polymer composite. So the first lecture in this week will be FRPC, that is fiber reinforced polymer composite in flexural strengthening of structural members. First part A, okay, 1. So in this lecture, we will cover the concept of FRPC in strengthening of structural components and flexural strengthening of structural members. So the strengthening or retrofitting of existing structural components, so that is basically used to resist higher design load, to correct strength loss due to deterioration, to correct design and or construction deficiencies, to increase ductility and to increase durability. So the fiber reinforced polymer composite has various uses in structural applications because they are corrosion resistant, they have lightweight, they have high strength to weight ratio, they have high strength and stiffness, they are durable, and they are easily fabricated, erected, and constructed. So the uses of FRPC in structural applications can vary uh, as per the requirements. So they can be used as plates or strips, that is at a face to improve the tension capacity, as bars in reinforcement in members like beams and slabs, replacing steel bars, as cables, that can be used as tendons and post tension members in suspension and bridge girders, and as reps around columns as confinement to improve the compressive strength and ductility. So it can provide, it can basically strengthen, it can be used as a retrofitting of structural components for strengthening of the flexure, shear, and axial uh, force, basically the axial, shear, and flexural components. Okay, and the strengthening of structural components can be done using by using it as structural members in beams, slabs, columns, joints, and walls. So, in case of flexural strengthening, it can be used to increase the tensile or flexural resistance of existing concrete beams or slabs, bonding FRP strips or fabric or laminate to the tension face of the flexural member with fibers oriented along the length of the member, bonding FRP bars to the tension face of the flexural members along the longitudinal reinforcement near surface mounting. Okay, so that is basically NSL, which is basically bonding of FRP bars to the tension face of the flexural members along the longitudinal reinforcement. So that is how it can be used as flexural strengthening. So for the case of shear strengthening, it can be used to increase the shear resistance of existing concrete members, for partial or complete wrapping of the members with FRP strips or fabric, for orienting fibers transverse to the axis of the member or perpendicular to the potential shear cracks, and for using it as axial strengthening, it is basically done to increase the axial resistance of existing concrete columns, to increase the ductility of existing columns, for complete, partial, intermediate wrapping of column members with FRP of single or multiple layers. So let us start with flexural strengthening. So the investigations on flexural strengthening of concrete members. So different types of FRP composites like GFRP, AFRP, CFRP can be used. Then different forms of FRP composites like sheets, laminates, strips. Then different orientation, pattern, and thickness of FRP. Different types of bonding between existing concrete and FRP using various adhesives and mechanical anchorages. And different types of uh, concrete members like flexure dominated member and shear dominated member. Okay, so these are the various uses, the types by which it can be used for flexural strengthening. And various various characteristics can be to estimate the increase in the flexural capacity of the member, to determine the failure modes of flexural member, to determine the ductility and serviceability limits of member, to estimate the effects of environmental variations for different loading conditions, which can be monotonic and cyclic loading basically. So this is for example of details of test beams which have been strengthened with FRP It has been taken from a literature from 1991, which was uh, headed, which was basically authored by Ritchie, a person called Ritchie. So this is the increase in flexural capacity of beam member. Okay. So as per that literature, this was the moment versus deflection plots basically, as can be seen here. So this is the mid-span moment, and this is basically a plot between mid-span moment and deflection for the control beam and the third beam C, which obtained both experimentally and theoretically. So the deflection was less, and they were able to take a more mid-span moment, okay, as compared to the control beam, okay, which was not retrofitted basically. So this is a typical plate failure through concrete. This is the concrete crushing in constant movement region. And this is the external plate failure. And this is the end of double angle failure through concrete. Okay. So these are the various failure pattern of beams. So here the different amount of FRP strengthening. Okay, so as per the this literature, so they use concrete beams having 76 by 127 by 1350 mm dimension, compressive strength of 44.7 megapascal, steel reinforcement which had 2 to 4.6 millimeter diameter bars, stirrups of 4.6 mm diameter at the rate 40 mm center to center, CFRP tensile strength of 1450 megapascal, elastic modulus of 186 gigapascal, and CFRP thickness of 0.2 mm, 0.65 mm, 0.9 mm, 1.9 mm respectively. So this is the schematic of the FRP strengthened beam basically. So this is the load deflection response for the different amount of CFRP strengthened beams. So as you can see, so basically the fiber reinforced polymer used beams basically, so they had a high load carrying capacity and lesser deflection. Okay, and this is the influence of FRP and steel reinforcement on failure mechanism basically. So again, one more literature from 1994, so it has showed different types of FRP composites, that is AFRP, GFRP and CFRP. Okay, so these are some of the detail. Okay, and these are the details of the test beams used. So they also, if you see, so stress strain response of different FRP composites have been shown. So this basically A represents aramid fiber reinforced polymer. This G is basically glass fiber reinforced polymer, and C is basically carbon fiber reinforced polymer. Okay, so so in this case it has been also graphite. Okay, G. So it can be various types, so a glass, gypsum, graphite. Okay, it can be of any type. Okay, so in here I think it has glass has also been used apart from graphite has also been used apart from glass. Okay, so these were the various stress strain responses of different FRP composites, and this is the load midspan load as a function of midspan displacement. Okay, so load displacement response for different FRP strengthened beams. So these are the various failure modes. Okay, so control beam. So this has been like concrete crushing. Okay, so here only concrete crushing has occurred. In AFRP strengthened beam, crushing as well as debonding has occurred. In GFRP strengthened beam, fabric tensile failure occurred. In CFRP strengthened beam, fabric tensile failure. Okay, so these were the failure modes basically. So again, one more literature. So it used different amount of FRP strengthening. Okay, and these are the details of test beams used and various characteristics of the materials used. So here also, if you see effect of number of CFRP layers on beam deflection. So basically they had different layers being used. So higher was the layer of CFRP, more was the applied moment, okay, moment carrying capacity, and lesser the midspan deflection. So here again, then here it has been shown the effect of number of CFRP layers on serviceability, okay, and also the effect of number of CFRP layers on midspan strain. Okay, so the values reduce with more moment carrying capacity. So that literature said that for various beams, for various your reinforced FRP reinforcement modes, layers, basically the mode of failure was different. For the standard, it was under reinforced beam failure followed by concrete crushing. For one layer, it was concrete crushing and splitting of CFRP. For three layers, it was concrete crushing, splitting of CFRP and minimal bonding. And for 5 layers, it was concrete crushing, splitting of CFRP and ductile failure with minimal debonding. Okay. So now so they also showed the crack pattern basically. So control beam showed widely spaced cracks. Okay, so this was the control beam, and beams with CFRP showed cracks at relatively close spacing. Okay, and it led to CFRP rupture and then concrete crushing. Okay, so that was basically the pattern how the failure occurred. In summary, we could say from this lecture that we studied about the FRP in structural applications, the flexural strengthening of concrete beams, that is, the influence of FRP composites on flexural response of concrete members, load deflection responses, moment deflection responses, load moment strain responses of FRP retrofitted members, and failure modes of FRP retrofitted members. So these were basically studied in this lecture. So the next lecture will be a continuation, that is FRPC of flexural strengthening in structural members, part B. So here we will be basically continuing the flexural study of flexural strengthening of structural members. So here again, as we studied, so investigations on flexural strengthening can be of different, using different types of FRP composites, different types of FRP forms of FRP composites, different orientation, pattern, thickness, different types of bonding, and different types of concrete members. Okay. So one more literature basically, so it showed the different types of flexure members as can be seen here. So this was a flexural beam, this was a shear beam. Okay, and basically this was the detail, these were the details of the test specimens. Okay, so the CFRV composites with fibers oriented at different angles have been provided, and epoxy resins of two different types have been used in that literature. So these were the different FRP strengthening schemes on beams as could be seen here. Okay, and these were the details of the section. So they also found improvement in envelope flexural beams. Okay, so this envelope was high. Okay, so that is basically it was able to have a high toughness. Okay, so toughness is basically the energy it could take per unit volume. Okay, so per unit amount of volume, what is the energy it could take. So that is basically the area under the stress and the deflection. Okay, so if you could see here, so it was quite high. Okay, as compared to the control beam, and the improvement in envelope shear beams were also found. So it was also higher, but lesser as compared to the flexural beams, and the typical FRP stress strain relationship for various fiber orientations have been shown here. Okay, so they also showed the failure modes. Okay, so this was the failure of flexural beam, this was shear beam at failure, this was the mechanism of FRP plate delamination. So delamination was the separation of the surface layer. Okay, and so this was a flexural shear crack enlarged for clarity. So if you remember, the shear cracks were always the diagonal cracks and flexure was the tensile cracks. Okay, so it was a combination of both, so it is a flexure shear crack. Okay, and this is a control shear beam at failure. Okay, so these were the values basically. Okay, now uh, basically your different beam so this is one more literature. Okay, so it basically tried to find the different beam conditions, okay, and surface preparation. So as can be seen here, and these were the details of test beams, okay, for a concrete having compressive strength of 36 megapascal, and the surface preparation was done by sanding, sandblasting. Beam condition was virgin or unloaded pre-crack, so very like sound specimens, and CFRP of 1 ply 2 ply. So these were the number of layers basically, and this was the result basically. So this was load versus midspan. Okay, load versus midspan, and deflection plots for CFRP strengthen, members, right? So this was the load versus the midspan deflection plots for CFRP strengthened beams. Okay, so this also had a similar observation, and these were the failure mechanisms for various different strengthening schemes as per the literature, as you can see. So one more literature that was this investigation was done in 2000 by Ramana and the team. So these were the different levels of strengthening, okay, and these were the details of test beams, and the beams were 100 by 100 by 1000 dimension and having a compressive strength of 30 megapascal, and these were the specifications. So here also you could see the effects of different levels of FRP strengthening basically. So there are different effects of different volume of different levels of FRP strengthening can be seen here, and the different levels of strengthening width of CFRP laminate of various sizes expresses percent of equivalent of balanced steel. Okay. So they found that the failure modes and crack pattern. So these were the failure modes and crack patterns of strengthened beams. So you could see that control beam shows widely spaced and lesser number of cracks. Okay. So widely spaced. So this was the control specimen. So the cracks were widely spaced and lesser number. Okay. And beams with CFRP showed cracks at relatively closer spacing. So as you can see the above ones. Okay, and at relatively closer spacing, leading to peeling of CFRP laminate. Okay, the CFRP sheet got peeled off. Debonding taken place due to flexural shear cracks with cracking sound. Okay, so debonding is basically the peeling off, delamination. Okay, so one more study in 1997 by Norris. So it showed the internal force, strain, and stress diagrams of FRP strengthened concrete beam. Okay, so this was the analytical study, and here it was found that FRP strip sheet laminate can provide increase in strength, stiffness, and ductility of existing beams when bonded at the tension phase of the member. Okay, and increase in strength depends on the amount, orientation, type, and strength of FRP composites. Higher is the amount of FRP strengthening, more is the increase in strength, and however higher is the amount of FRP strengthening, less is the ductility. So more is the FRP strengthening, increase is the strength, which is quite trivial, but lesser is the ductility. Okay, an increase in strength is maximum when the fibers are oriented along the length of the member, least when it is perpendicular, and intermediate when oriented at an angle to the member. Okay, so basically fibers need to be oriented along the length of the member for maximum strength, and least it will be when it is perpendicular, and intermediate when it is at an angle. The performance of a strengthened pre-crack specimen without sealing the cracks is not significantly different from that of a strengthened virgin or sound specimen, unstressed. And considering concrete surface in good conditions, so the effectiveness of surface preparation using sanding or sandblasting appears to be slightly in favor of the latter. The increase in ultimate strength is greater for wrap beams with a lower percentage of steel reinforcement than for those with a higher percentage of steel reinforcement, and the deflections for the FRP retrofitted beams exhibit a significant reduction with increasing number of layers. Okay, so that is also quite obvious. So more is the number of layers, lesser is the deflection for the FRP retrofitted beams. The strengthened laminated beams exhibited more number and closely spaced cracks as compared with the several widely spaced cracks for control beams, which we saw in that figure. And this showed that the retention of composite action and increased serviceability from the CFRP laminates. Cracks at relatively closer spacing led to peeling off of CFRP laminate. Debonding had taken place due to flexure shear cracks with cracking sound. The failure of FRP retrofitted beams may be due to debonding or peeling of FRP, rupture of FRP, steel yielding, or crushing of concrete. So this basically is this again is taken from a literature from an investigation uh, performed by Bocchiarelli in 2013. So it shows the schematic of failure modes of FRP strengthened members. So this is the FRP rupture, this is the crushing of compressive strength, this is shear failure, this is concrete cover separation, and interfacial debonding, intermediate flexural crack induced interfacial debonding, intermediate flexural shear crack induced interfacial debonding. So these are the various failure modes. The failure mechanisms of FRP retrofitted beams are generally: A. Steel yield FRP rupture, B. Steel yield concrete crushing, C. Debonding either at the interface between concrete and FRP or through the concrete layer between the FRP and the steel reinforcement, and D. Concrete compression failure. Okay, basically 4 types. So that was basically this lecture, which basically studied the flexural strengthening of FRPC strengthened structural members. Okay, so the next lecture will be FRPC's shear strengthening of structural members. So in the last lecture, we basically last lectures we basically studied the influence of different types of FRP composites like GFRP, AFRP, CFRP with different fiber orientation, pattern, and thickness of FRP composites on different types of concrete members like flexure. Basically, okay. So now we will be flexure and shear dominated members. It was shown, but now we will study the shear strengthening. Okay. Further, we studied the load deflection responses, moment deflection responses, load moment strain responses of FRP retrofitted members, and failure modes of FRP retrofitted members. So in this lecture, we will be basically covering the shear strengthening of structural members. So shear strengthening was basically done to increase the shear resistance of existing concrete members for partial or complete wrapping of the members with FRP strips or fabric, orienting fibers transverse to the axis of the member or perpendicular to the potential shear cracks. Okay. So the investigations on shear strengthening of concrete members can be focused on different types of, it can be based on different types of FRP composites, different forms of FRP composites, different orientation, pattern, and thickness, beam type, geometry, and concrete strength, and quality of existing surface of concrete. So these are the parameters. So it is almost similar to the flexural strengthening. And it is done to estimate the increase in the shear capacity of the member, to determine the ductility and serviceability limits of member, to determine the failure modes of the member. So these are the main uh, aim of the shear strengthening. So if we go to a literature from 1998 of Khalifa, done by Khalifa. So here you could see the increase in shear capacity of beam member. So this is totally wrapped. Okay, this is U jacket and this is bonded to sides only. Okay, so the double lines basically, so that basically means the shear strengthening. Okay, so the wrapping. Okay, so this is total, it contains, so basically it is a complete rectangle. Okay, so it is totally wrapped. If it is only like U shape, it is U jacket, and if it is only bonded sides, so it is bonded to sides only. So this is bonded surface configuration. Then there is FRP reinforcement distribution in continuous sheet and strips. Here it is fiber orientations. Okay, 90-degree, 45-degree, and so you can see it is 90-degree and this is 45-degree. And then there is 0 to 90 degree. So this is pseudo isotropic FRP reinforcement schemes, and this is again plus minus 45. So it is like X. Okay, X shape. And here if you see there, it is here it has been shown about mechanical anchorage options. So here it does not have any anchors, so no anchors, and here mechanical end anchors are provided. Okay, so these are the different FRP shear reinforcement configurations. So again, if we take from literature of 2007, which was been performed by Tang and Chen, so it shows different FRP shear reinforcement configurations. So this is fiber orientation and distribution, and this is the bonding scheme and notation. So as you can see, different methodologies have been applied and different shear reinforcement configurations have been adopted. So this study was performed by Katslakev and McCurry in 2000. So here it shows full-scale beams of different types, and this was the detail of test beams. So beams were 305 by 762 by 6096 mm dimension and had a compressive strength of 20.7 megapascal. And basically the test beam A control beam was basically for typical beam with shear stirrups and flexural steel, flexural only, that is control with added flexural carbon CFRP reinforcing. Your shear only was control with added shear GFRP reinforcing, and shear and flexure was control with added shear GFRP and flexural CFRP reinforcing. Okay, so basically this was the shear strengthening. These were the characteristics of the fibers used, and these were the various beams and their failure modes. Okay, so control diagonal tensile tension cracks had appeared, that was the shear failure, and flexural only was also similar, diagonal tensile tension cracks. In your this one shear only, here yielding of tensile steel was followed by crushing of compression and concrete after extended deflections. And in shear and flexure beam, so not observed, possibly due to yielding of tensile steel followed by crushing of compression concrete. So these were the various load maximum. So this figure showed the load versus maximum deflection responses, and this figure showed the load versus strain responses basically. So the basically the S only, that is shear only beam, had the maximum deflection. Okay, and whereas the shear, and so the shear only beam had a maximum deflection but a higher load carrying capacity, okay, as compared to the control. And the flexure only also had the lesser than shear only deflection but higher than shear only more load carrying capacity. Okay, and the shear and flexure both carrying beam, so that had deflection similar to control beam and very high your moment carrying capacity. So this was also found here as well. Okay, so they basically showed the cracking and failure of this. These authors basically showed the cracking and failure of test beams. So this was the failure mode in a control beam. Okay, so this was the shear only beam. Okay, and so this was basically the shear and flexure beam. Okay, so you could see both lines. One is the diagonal line. This is the shear line, diagonal line, and this is the tension. Okay, and here only flexure only beam. Okay, so it had mainly the flexure. Okay, so one more study done by Khalifa in 2000. So they basically saw the full scale beams with different parameters. So they use steel stirrups with and without steel stirrups, shear span to depth ratio, A by D ratio 3 and 4, CFRP amount and distribution, continuous and intermittent, CFRP pattern, and lateral two-sided and U-rep, CFRP orientation 90 degree and 90 degree only, and N anchor, U-rep with and without N anchorage. So these were the details of test sections as have been provided in that investigation research paper, and these were basically the results. So they showed the simply supported beams with 90 plies A by D 3 equal to 3, simply supported beams with 90 plies A by D equal to 4, simply supported beams with U reps of different spacing A by D equal to 3, and your simply supported beams with U reps of different spacing A by D equal to 4. So various ratios were basically used. Okay, span to depth ratios. Okay, and again these were for the continuous beams and as well as simply supported T beams. Okay, with varied plies. So these were basically the failure modes. Okay, as observed by the investigation, from the investigation. So this was the investigation. This was the result for debonding of CFRP over shear crack. So above the shear crack, this debonding had occurred. This was the debonding of CFRP below shear crack. So this was the shear crack. So below this, the debonding had occurred. This was the simply supported concrete splitting. So the splitting of concrete had occurred. Okay, so it was for the simply supported case, and this was continuous flexural failure. Okay, so for continuous beam, flexural failure had occurred. So as you can see, the beam has fallen by flexure. So this is the straight line. Okay, so the tension crack. Okay, so these were the differential strengthening schemes as could be seen here. So basically they use 4-point loading. Okay, so 4-point loading, and the beams were so this was one more study for to find out their different shear strengthening schemes performed by Lee and others in 2001. So beam day used was 130 by 200 by 1350 mm dimension, and concrete was having a compressive strength of 37 megapascal. The CFRP sheet was 0.5 by 120 by 1040 mm, and elastic modulus of 120 gigapascal, and failure strain of 0.8% was used for the test beams. Okay, so this was the experimental beam with strain gauges, and these were the results of load versus strain at bottom of CFRP sheets, and this was the load versus maximum deflection. Okay, so these were the failure modes and crack patterns. So this was beam A after the failure. This was beam B, C, D, and E. Okay, so these were the beam cracks after failure. And so further, one additional study done by Mofidi and Chalal in 2011. So they studied the effect of strip width to strip spacing ratio. So what was the effect of strip width versus strip width divided by strip spacing ratio on the performance? Okay, for that they so these were the details of test beams with different placement of FRP strips, and they use concrete having compressive strength of 29 to 31 megapascal, and series S0 beams had no steel stirrups. S1 had steel stirrups, and this was the W by S ratio, that is width to strip width to strip spacing. So basically width to spacing ratio. So 40 by 115, 87.5 by 175, then your, so that is 1 by 2 basically. So 53 by 87.5, 30 by 50, 87.5 by 125, and 1 by 1. And these were the characteristics of the material used. So this was the basically result. Okay, observation: load versus maximum deflection responses as could be seen here, with no steel stirrups and with steel stirrups. Okay, so these were able to take more deflection, that is it had a more toughness. Okay, toughness is the energy it could take per unit volume. Okay, so that was the more toughness. Okay, so that this type of structure are very good for earthquake. Okay, so we'll be studying in later classes about them. So then it was so these were the results for failure modes, with no steel stirrups and with steel stirrups. So you could see here that control beams failed in shear. All CFRP retrofitted beams failed in shear. Premature CFRP debonding followed by concrete crushing. Local CFRP fracture at the web due to stress concentration. So these were the observations. Then one more study was done to find the debonding of FRP strengthened beams, which was done by Chen and Teng from 2003. So these were the different FRP shear strengthening beams schemes as shown here. So the effect of strip width to spacing ratio on shear capacity of FRP strengthened beams has been found has been shown here, and the schematic of shear failure due to FRP debonding has been shown here. Okay, so this is side bonded FRP, and this is FRP U jacket. So if you see here, the in case of U jacket, the debonded zone was much higher as compared to the debonded zone in side bonded FRP. Okay, and however the shear crack was almost the same. Okay, so this was the effect of FRP strip location on effectiveness of shear strengthening. Okay, and the limit of clear strip spacing was also basically detailed by equation. Okay, so they found that shear failure of FRP strengthened RC beams involves development of a single measure or a number of diagonal shear cracks. Eventual failure is due to the tensile rupture of FRP and the debonding of FRP from concrete. Both failure modes starts with debonding from the critical shear crack. Tensile rupture starts in the most highly stressed FRP strip, followed rapidly by the rupture of other FRP strips intersected by the critical shear crack. Okay, for debonding type of failure, it is the sequential debonding of FRP strips starting from the most vulnerable strip. FRP rupture failure commonly occurs in beams with complete FRP reps and also with FRP U jackets. FRP debonding failure generally occurs in beams with FRP side strips and FRP U jackets. Mechanical anchors are used to prevent debonding and thus to change the failure mode from debonding to FRP rupture. The total shear resistance of FRP strengthened RC beams commonly consists of three components from concrete: internal steel shear reinforcement and external FRP shear reinforcement. Thus, shear strength of FRP strengthened beam Vn is equal to Vc plus Vs plus Vfrp. The two parameters are important in determining the FRP contribution. That is shear crack angle, which was generally assumed to be 45 degree, and average stress or effective stress in the FRP strips intersected by the critical shear crack. So, from this lecture, we can summarize about shear strengthening. So, we understood the influence of different types of FRP composites with different fiber orientation, pattern, and thickness on different geometry of concrete members. And also, we studied the load deflection responses, load strain responses, shear force displacement responses of FRP retrofitted members, and failure modes of FRP retrofitted members. So now let us go to the next lecture, which is basically FRPC in axial strengthening of structural members, the first part A. So here we will be basically covering axial strengthening of structural members. So axial strengthening is required to basically increase the axial resistance of existing concrete columns, to increase the ductility of existing columns, for complete partial intermittent wrapping of column members with FRP of single or multiple layers. This is a typical behavior of uniaxially loaded unconfined concrete. So as can be seen here, so this is a tension, compression and stress pattern. Okay, so stress versus strain pattern for both compression and tension in unconfined concrete, and this is the stress strain responses of concrete under various confinement levels. Okay, so it can be seen here. So with the increase in confinement, the stress carrying capacity also increases. So the factors of influence, okay, in axial strengthening using FRP wrapping can be levels of confinement, types of confinement fibers, FRP wrapping scheme, length of column or slenderness ratio, type of cross section of column, bond between concrete and FRP, and grade of concrete used. Okay. The investigation on axial strengthening of concrete columns was done firstly to estimate the increase in axial capacity of columns, secondly to estimate the increase in ductility of columns, and thirdly to determine the failure modes of columns. So basically, so this study was done for finding the levels of confinement effect based on impact of levels of confinement. So it was done in 2002 by Moitro and Mukherjee. Okay, so this were the specifications of the fiber type, which was e-glass fiber, and the circular columns was were diameter of 100 mm by length of 300 mm, and it had a compressive strength of 20 megapascal concrete, and column confinement was 0, 1, 2, 4, 8 layers of GFRP. The FRP wrapping thickness was 0.4 mm, 0.8 mm, 1.6 mm, and 3.2 mm, and the fiber orientation was 0 degree. So the levels of FRP confinement, its impact was shown here. So these were the stress strain responses. So more was the number of layers used. So higher was the axial stress carrying capacity and also axial strain carrying capacity. So axial stress versus axial strain for columns having different levels of FRP confinement. And here it shows the axial stress versus lateral strain. So here axial stress versus lateral strain for columns having different levels of FRP confinement. So here also the thickness was basically up till 3.2 mm. It had a good this one. It has a proportional positive impact. How so? Sorry. So with increase in thickness, it has a positive impact. Okay. Although at 1.6 mm, the lateral strain carrying capacity was less. Okay. Apart from that, the axial stress was always high. So these were the failure modes basically. This is the typical left failure mode of specimen with one layer of 0.4 mm thick wrap. This was concrete specimen after removal of wrap. This was typical fiber rupture failure mode of specimen with 0.8 mm, that is 2 layers, and 1.6 mm, that is 4 layers wrap. Okay. So this was basically so now let us see the types of confinement fibers. So its impact, okay, different fibers impact. So this study has been taken from Tautanzi and Safi. Okay, they performed this in 2002. So three types of composites: glass FRP, aramid FRP, and carbon FRP. Okay, so these three types of composites were used, and these were the specification. So it had varying confinement with intermittent wrapping. FRP hoop spacing ranged from 30 to 78 mm. So this was a test setup of PVC FRP confined concrete columns, and the circular columns cast within PVC tubes had 102 mm diameter and 305 mm length, and the concrete had a compressive strength of 45 megapascal in average. So these were the results, basically the stress strain relationship. So this is the GFRP confined column, this is the AFRP confined column, and this is the CFRP confined columns. Okay, so lower is the hoop spacing of FRP, higher is the increase in axial strength. Okay, so less is the hoop spacing, higher is the increase in axial strength. So they found that these were basically the failure patterns of PVC FRP confined concrete columns. So they found that failure of spacing by failure of 1/2 FRP hoops at the middle or bottom half of specimen, accompanied by failure of PVC tubes, and for larger FRP spacing, failure of specimen by shear failure of concrete core and PVC shell, followed by FRP hoops. Okay. So now next, basically the study on the type of FRP wrapping scheme. So this was taken from an investigation done by Howie and Karbhari in 1995. So these were the basically the details of the specimens used, and concrete. So basically circular column was used, which had a diameter of 152.4 millimeter and 4.8 millimeter height. Okay, and the compressive strength of 41.38 megapascal was used, and FRP properties had were like it had a tensile strength of 3500 megapascal and tensile modulus of 227 gigapascal. The wrapping schemes were 9 numbers with varied fiber orientation and layers. The maximum strength and axial strain for specimen with FRP 0, okay, 4. So this was the angle basically, and maximum radial strain for specimen with FRP 0, 90, 0. Okay, so this was the pattern. Okay, so then the length of column. Okay, so for this basically we the study basically taken is performed by Mirmiran in 1998. Okay, so these were so they studied for varying slenderness ratio. Okay, so that is the length of column. So the fiber uses e-glass fiber, and this is its characteristics. So the FRP tube thickness used were 1.545 mm 6 plies, 2.21 mm 10 plies, and 2.97 mm 14 plies. The column diameter was 152.5 millimeter. The length of column was 305 mm, 457 mm, 610 mm, and 762 mm. And the length by diameter L by D ratio was 2:1, 3:1, 4:1, and 5:1. So the results have been shown here. So this is the stress strain variations for FRP confined columns of varying L by D ratios, and this is the normalized ultimate strength versus L by D ratio. Okay. So they saw basically the length of column basically were 305, 813, 1372, 1651, 2286, 2591, 2743 mm, and compressive strength of 22.4 megapascal was used. And this was the stress strain variation for FRP confined columns of varying slenderness ratio. Okay, and this was the failure pattern of the slender column. So it could be seen that buckling failure had obtained, obviously. So with higher slenderness ratio, that basically means a higher probability of buckling. Okay, so buckling failure occurred, rupture of FRP away from mid height. Okay, so the rupture had basically occurred away from the mid height. So then the length of column was again performed by Mukherjee and Moitra in 2004. Okay, and this is the characteristics of the fiber used. So the FRP confinement basically had one layer of GFRP, 4.4 millimeter thickness and 0-degree fibers, and basically two types of columns, short circular column and long circular columns basically were used. Okay, so short circular columns had sorry, the short circular columns had basically a diameter of 100 mm and length of 300 mm, and long circular columns had basically diameter of 100 mm and length of 750 mm, and concrete had a basically compressive strength of 20 megapascal. Okay, so this is basically the axial strain versus axial stress for short and long columns, as could be seen here. So as expected, the long column basically had a lesser axial strain and axial stress carrying capacity. However, the short column had almost twice, okay, twice the axial strain carrying capacity, more than twice, and even higher axial stress capacity. However, the failure pattern up to, however, the behavior as per uh, the behavior of both the long and short columns was almost the same, okay, up to the point of failure of the long column, basically. Okay, now these were the failure modes basically for the short column and long column. The short column, and so here the failure occurred here, okay. So you could see here the left failure away from mid height, okay, as could be seen, and concrete crushing at the failed region. So at the failed region, the concrete has also crushed, okay. So in both the cases, and you could see that longer was the column, more far was it from the mid height, okay. So in summary, we could say in this lecture we studied about axial strengthening. So we studied the influence of FRP, levels of confinement, types of FRP confinement like AFRP, GFRP, CFRP, types of fiber orientation and pattern, and slenderness of concrete columns. The axial strain response, axial strain, lateral strain responses of FRP retrofitted members, and failure modes of FRP retrofitted members. So basically, we studied about all this, okay, and your this one. So that was all about that lecture. So next lecture also will be continuing the FRPC in axial strengthening of structural members. So here we'll be basically again continuing the previous lecture discussion. So we studied that basically the influence factors for axial strengthening in FRP wrapping is level of confinement, type of confinement fiber, FRP wrapping scheme, length of column or slenderness ratio, type of cross section of column, bond between concrete and FRP, and grade of concrete. So we studied up till your length of column, slenderness ratio. Now let us see the effect of type of cross section. So this information has been taken from a study from Mirmiran in 1998. So basically they took both circular and square sections. So if you see here, basically, so these were the specification of the fiber. So fiber tube thickness used was 1.4 mm, that is 6 plies, 2.21 mm 10 plies, and 2.97 mm which had 14 plies. The circular column had a diameter of 152.5 mm and 305 mm your height. The square column had, oh, sorry, so it was the height. The square column had 152.5 mm the edges and 305 mm height, and corner radius was 6.35 mm. The compressive strength for circular column was 30 megapascal, whereas for square column it was 40 megapascal. So basically this was the results of the axial stress versus axial strain response for circular and square column, as could be seen here. So basically square and circular, so the circular basically performed much better, okay. Square had like it was like almost of a, the behavior was similar, little bit similar to that of a your steel bar, okay. So that basically had a that yielding point, okay, and after that elastic limit it basically tried to reduce its strength, okay, where however the circular column kept on increasing. So basically, this was the failure modes of both the columns. The circular column, in the circular column, rupture of fiber near the mid height had taken place basically, whereas in square column, rupture of fiber at the corners, okay, away from mid height. Okay, so that was the difference. And the type of cross section study was also performed by Mukherjee and Moitra in 2004, where they took 3 sections instead of 2. They also included a rectangular, circular, square, and rectangular. So these were the characteristics of the fibers. So FRP confinement of one layer of GFRP. Circular columns used was 100 mm diameter and 750 mm length. and square columns were 100 mm side and length of 1000 mm. The corner radius was 5 to 7.5 millimeter, and rectangular columns were 85 mm into 180 mm cross section and 850 mm length, and corner radius was around 5 to 7.5 millimeter. So uh, basically non-circular section had a, it was found that non-circular sections had a influence of corner radius. Okay, so effect of corner radius on axial stress for non-circular sections. Okay, so more was the corner radius, lesser was the corner stress. Okay, and this is the FE model of non-circular column with corner radius, if you can see. So with increase in corner radius, the stress concentration reduced drastically. Okay, and this was the stress strain responses of FRP confined columns of different cross sectional shapes. Okay, so here however, if you could see, so this was little bit the study actually was it basically countered the earlier study. Okay, so in the earlier study, if you remember, the square section had a very limited yielding point. Okay, and after that it basically came down. Okay, but here it is going, okay, it is going proportionally only, although the rate has started decreasing after reaching the elastic limit. Okay, so these were the failure modes of circular column and your rectangular column. And your this circular column, basically left failure away from mid height had taken. Okay, and in your rectangular column, rupture of fiber at the corners away from mid height. So both had your rupture away from mid height. Okay, which was not the case in the earlier study. There it was found in circular column, it was in near the mid height, whereas in the square column it was near the away from the mid height. Okay, near the corners. But here both the failures had occurred away from the mid height. For circular column it was left failure, and for rectangular column it was rupture. Okay, and concrete crushing at the failed region had also occurred. So next, also for non-circular section, one more study was performed by Lam and Teng in 2003. So they also saw the type of cross section, basically non-circular section. So they took various types of section. One was FRP, like they used FRP wrapping of 1, 2, 3, 4, and 5 layers. Circular column they used having dimension 152 mm diameter and 610 mm height. Square column used was 150 by 150 cross section with 600 millimeter height, and rectangular column had 150 by 225 mm cross section with 600 mm height. The corner radius was 15 mm and 25 mm, and compressive strength of 24, 33.7 and 41.5 megapascal was found. So these were the stress strain responses basically of corner radius 15 mm and corner radius 25 mm for square column of varying layers of CFRP. And more, it was again found that more is the your, if you could say, more is the corner radius of column, higher is the axial strength. Okay, so this was much higher than this. And also they showed the stress strain curves for rectangular column with 4 layers of CFRP. So more is the corner radius of column, higher is the axial strength here also. And so you can see here the 25 was higher. Okay, and this is the effective confinement area for non-circular sections. Okay, so this is the effective your non effective confinement area for non-circular sections. Okay, although we have provided it at the edge. Okay, then so basically from here also you can see that more is the radius, more will be the radius, higher will be the your this one, higher, lesser will be this region. Okay, lesser will be the non-effective region. If the radius is more, then the region will be much lesser. Okay, then your this one, the type of cross section again for so this was the study. Okay, so continuing that study, this was a square column and this was a rectangular column. So in rectangular columns, rupture of fibers at the corners had taken near the mid height. Okay, so near the mid height it had taken in the rectangular columns. So the axial strain and lateral strain of concrete columns increase due to FRP confinement. Higher is the level of confinement, higher is the increase in strength, but lower is the lateral strain. And your this one, FCFRP is the most effective in increasing the ultimate strength, while GFRP is effective in increasing the ultimate strain. Okay, so CFRP most effective for ultimate strength and GFRP most effective for ultimate strain. Okay, increase. And effectiveness of confinement is maximum when fibers are oriented along the hoop direction, that is 0 degree, that is the transverse direction. Okay, failure of FRP confined columns is due to lap failure for single layer of FRP wrapping, while for multiple layers of wrapping it is due to rupture of fibers. The FRP confinement is most effective for circular columns as compared to square and rectangular columns. The ultimate strength and strain are less for non-circular sections. Failure of non-circular columns take place at the corners due to stress concentrations at the corners. Rupture of FRP take place at the corners. So corners should be rounded off to reduce stress concentration. Basically range of corner radius, okay, should be between 15 mm to 25 mm. Okay, so that will increase the confinement area zone. Okay, effective confinement zone. For circular columns, higher is the diameter, lower is the effect of confinement. For non-circular sections, the effectiveness depends on the lateral dimensions or the aspect ratio, h by b ratio of the column. For non-circular sections, the effectiveness depends significantly on the corner radius of the column to avoid stress concentrations at the corners. More is the corner radius, more is the effectiveness of confinement. Effectiveness of confinement depends on the slenderness of column. Higher is the L by D ratio, lower is the increase in strength and lateral strain. Okay. The confined concrete strength depends on the effectiveness of confinement, the initial concrete strength. The effectiveness of confinement depends on the elastic modulus of FRP, EF, the thickness of FRP wrapping, TF, initial modulus of concrete core, ECO, and the dimensions of the column D or B. Analytical models have been developed by researchers to define confined concrete strength FCC, literal confining pressure FL, and ultimate compressive strain epsilon Cu of confined concrete. So as per the study from Lemon Teng in 2003, so this is a stress strain model for confined concrete. Okay, so this is FRP confined concrete provided by Lemon Teng. Okay, this one, and this is the unconfined concrete, which is as taken as per Eurocode 2. Okay, so the lateral confining pressure is FL equal to N1 into EF into epsilon FU by D, and confined concrete strength is FCC equal to N3 into FCO plus K1 into F1. So FL. So these are some of the formulas which have been determined, okay, empirically. So you don't have to remember, okay, you don't have to memorize all this. So these are for your knowledge, okay. And maximum compressive strain epsilon Cu is equal to epsilon Co into 1 plus N2 into K2. Okay, so these are some of the relations used. So in summary, if we can say about this lecture, we continued our discussion on axial strengthening, and we studied the influence of FRP levels of confinement, types of FRP confinement like AFRP, GFRP, CFRP, types of fiber orientation and pattern, slenderness ratio and cross-sectional shapes of concrete columns, axial stress, axial strain response, and axial strain lateral strain responses of FRP retrofitted members were also studied, and failure modes of FRP retrofitted members were also seen. So with this, we come to the end of the discussion part. Now let us go to the solve problems section. So the first question, in case of shear strengthening of concrete beams using FRP, A. Investigations are carried out to determine the ductility and serviceability limits of member. B. Fiber orientation should be parallel to the axis of the member. C. Only complete wrapping of the members is done with FRP strips. And D. All of the above. So which is the correct option or statement for the shear strengthening case in concrete beams using FRP? So if you see the first statement, investigations are carried out to determine the ductility and serviceability limits of member. So that is true. Okay, investigations on shear strengthening of concrete member is done to determine the ductility and serviceability limits of member. Okay, the second question, sorry, the second point, fiber orientation should be parallel to the axis of the member. So that is not correct. So orienting fibers transverse to the axis of the member or perpendicular to the potential cracks. Okay, so it is transverse. So that is not parallel. So B is incorrect. So if B is incorrect, D is also not correct. And C, only complete wrapping of the members is done with FRP strips. So that is also wrong. Partial or complete wrapping both can be done of the members with FRP strips or fabric. So C is also wrong. So the correct option is A. So A, investigations are carried out to determine the ductility and serviceability limits of member is the correct option. Second question, choose the correct option regarding flexural strengthening of concrete beams using FRP. A, the increase in ultimate strength is greater for wrap beams with a higher percentage of steel reinforcement than for those with a lower percentage of steel reinforcement. B, the increase in ultimate strength is greater for wrap beams with a lower percentage of steel reinforcement than for those with a higher percentage of steel reinforcement. C. Deflections for the FRP retrofitted beams exhibit no reduction with increasing number of layers. D. None of the above. So, which is the correct option? Okay, for flexural strengthening of member beam concrete beams using FRP. So, if you remember, the increase in ultimate strength is greater for wrap beams with a lower percentage of steel reinforcement than for those with a higher percentage of steel reinforcement. Okay, so basically, this so the strength is more for lower percentage of steel reinforcement. Okay, so this is not for higher percentage. So A is not correct. B is correct. Okay, B is the right option. And if you see C, deflection for the FRP retrofitted beams exhibit no reduction with increasing number of layers. So that is also incorrect because FRP strips, sheets or laminates can provide increase in strength, stiffness and ductility. So stiffness is also increased. So more is the stiffness, lesser will be the deflection. Okay, so it exhibits reduction. Okay, so it is no reduction is incorrect. So C is also incorrect. So correct option is B. So therefore B, the increase in ultimate strength is greater for wrap beams with a lower percentage of steel reinforcement than for those with a higher percentage of steel reinforcement. Third question, in case of flexural strengthening of concrete beams, the strengthened laminate beams exhibit dash space cracks as compared with the several dash space cracks for control beams. Okay, so which is the correct option? A, closely widely, or B, widely closely. Okay, so if you remember, we had seen in a picture. So the strengthened laminated beams exhibited closely spaced cracks. Okay, so, space cracks and with a higher number as compared with the several uh, widely spaced cracks with lower number for control beams. Okay, so for strengthened laminated beams it is closely, and for control beams it is widely spaced. Okay, the cracks. So A, closely widely is the correct option. Okay, so you can see here also the same similar thing is written. So A, closely widely is the correct option. Fourth question, depending on the wrapping pattern of a beam, identify the type of wrap beam. Okay, so is it A, for this is the example of the wrap beam. So what is it? Is it a shear only beam? It is a flexure only beam? It is a shear and flexure beam, or it is none of the above? Okay, so if you remember, here there are two lines. Okay, both the tension line and a diagonal line. Diagonal tension crack and diagonal crack. So diagonal crack refers to shear, tensile crack refers to flexure. So this is basically a shear and flexure beam. Okay, so this is the hint. Okay, so this is for the control beam, it is like this. For shear only beam, only the diagonal cracks. For flexure only beam, okay, only in the middle, only the vertical cracks. And for shear flexure beam, both the diagonal and the vertical. Okay, so it is the shear and flexure beam, that is C is the correct option. So C, shear and flexure beam is the correct option. Fifth question, in case of shear strengthening of a concrete beam using CFRP, which is carbon fiber reinforced polymer, identify the possible failure modes. A, debonding of CFRP over shear crack. B, debonding of CFRP below shear crack. C, concrete splitting. Or D, all of the above. So which is the correct option? So if you remember in this study, okay, related to shear strengthening done by Khalifa, okay, in 2000. So if the debonding of CFRP occurs over shear crack, it looks like this. So it can be for debonding of CFRP, it can be over shear crack. Okay, so it is all the correct is a correct option. Then the debonding of CFRP can be below the shear crack like this. So B is also a correct option. And then there can be for simply supported, it can be the in shear strengthening case, concrete splitting can also occur. C is also correct option. Okay. So therefore all the three are correct. So D all of the above is the correct option. So D all of the above is the correct option. Sixth question. In case of shear strengthening of a concrete beam using FRP, with increasing FRP strip width to spacing ratio, FRP contribution to shear capacity will A increase, B decrease, C remain same, or D anything can happen. So which is the correct option according to you? So if you remember that there was a figure, okay, so more is the spacing, the width to spacing ratio, if you remember, higher is the shear capacity, okay, it will increase. Okay, so this is the diagram, if you remember, so it is increasing. Okay, so A increase is the correct option. Okay, so A increase is the correct option. Seventh question, statement 1, in case of axial strengthening using FRP wrapping, higher is the level of confinement, higher is the increase in strength, and higher is the lateral strain. And your statement 2, effectiveness of confinement is maximum when fibers are oriented along the hoop direction. So 1 is correct, 2 is correct, both are correct, or none of them is correct. Okay, so which is the correct option? Okay, so if you remember, just now we discussed about axial strengthening using FRP wrapping. So here, with the higher level of confinement, the increase in your this is present. Okay, the increase in strength is found. Okay, but the increase in both strength and axial strain is found. Okay, but there is a decrease in the lateral strain. Okay, so there is a lowering of lateral strain, so therefore one is not correct. Okay, not higher. Okay, so one is incorrect. But and also second statement, effectiveness of confinement is maximum in fibers are oriented along the hop direction. So basically in the transverse direction, maximum effectiveness of confinement of fibers is found. Okay, so 2 is correct. Okay, so 1 is incorrect, 2 is correct, so therefore B, only statement 2 is correct, is the right option. Okay, so you can see here also your higher level of confinement, increasing strain but lowering in the lateral strain. Okay, and your this one, CFRP, your this one, effectiveness of confinement is maximum when fibers are oriented along the hoop direction 0 degree. So B, only statement 2 is the correct option. Question, in case of axial strengthening of non-circular columns using FRP wrapping, the effectiveness depends on A, lateral dimensions, B, corner radius of the column, C, slenderness of columns, or D, all of the above. So if you remember, in the axial strengthening of non-circular columns, all the three take part: the lateral dimension, the corner radius of the column, and the slenderness of columns. Okay, so here it is shown, non-circular columns effectiveness depends on lateral dimension, that is aspect ratio, the corner radius of column. Okay, it depends, and also for your effectiveness also depends on the slenderness, okay, of columns. So all the three are depending, it is depending on all the three. So D, all of the above is the correct option. So D, all of the above is the correct option. Ninth question, in case of axial strengthening of circular and non-circular columns using FRP wrapping, the effectiveness of confinement depends on A, the elastic modulus and thickness of FRP, B, the initial modulus of concrete core, C, neither A nor B, D, both A and B. So which is the correct option? Okay, so the effectiveness of confinement in circular and non-circular columns for the case of axial strengthening under FRP using FRP wrapping. Okay, so it depends on if you remember all the three. Okay, elastic modulus, thickness, and initial modulus of concrete core. So elastic modulus, effectiveness of confinement depends on elastic modulus, thickness of FRP wrapping, and initial modulus of concrete core. Okay, so D, both A and B are correct option. Okay, so D, both A, elastic modulus, thickness of FRP, and B, initial modulus of concrete core is the right option. So D, both A and B are correct. 10th question. In case of axial strengthening of non-circular columns using FRP wrapping, higher is the slenderness ratio, dash is the increase in strength and lateral strain. Okay, A higher, B lower. Okay, so if you remember, more is the slenderness ratio, lesser will be the increase in strength and lateral strain. Okay, so that is the case of axial strengthening of non-circular columns using FRP wrapping. Okay, so that is also written here. Effectiveness of confinement depends on the slenderness of column also. Higher is the L by D ratio, so lower is the increase in strength, and lower is also the lateral strain. Okay, so because of the higher confinement. Okay, so B lower is the correct, your this one, uh, lower is the correct option. Okay, so with this we come to the end of today's discussion. So hope you had understood the various retrofitting techniques using FRP members on concretes, okay, of various types. So let us meet next week again for continuing the sixth class. Okay, with this I would like to end today's discussion. Thank you.